Hey everyone, before we dive into today's incredible story, I need you to do me a quick favor. Hit that like button right now, smash that subscribe button, and drop a comment below telling me where in the world you're watching from. Seriously, I love seeing where our community is tuning in from, whether you're in London, Los Angeles, Tokyo, or anywhere in between. England, 1940. The Luftwaffe is pounding British cities night after night. The RAF is bleeding aircraft faster than they can repair them. Every hour counts. Every plane matters. Every rivet is critical. On an airfield somewhere in southern England, a ground crew mechanic stares at a damaged Spitfire. Dozens of bullet holes perforate the aluminum skin. Under normal circumstances, this repair would take 2 men hours upon hours of backbreaking work. But today, this mechanic has something new in his toolbox, something so revolutionary that within 3 years, 3 billion of them will be manufactured for the war effort. This is the story of the pop rivet. By 1939, the world stood on the brink of total war. Aircraft had evolved from fragile wood and fabric biplanes to sophisticated all-metal monoplanes capable of speeds exceeding 350 miles per hour. The Spitfire, Hurricane, Messerschmitt Bf 109, and American bombers represented the pinnacle of engineering. But there was a problem, a critical bottleneck that threatened to cripple Allied air power. Traditional aircraft construction and repair methods simply couldn't keep pace with the demands of modern aerial warfare. Every time a bomber returned from a mission over occupied Europe with battle damage, ground crews faced an agonizing choice: spend precious hours repairing the aircraft using conventional methods, or cannibalize it for parts and scrap the airframe entirely. The statistics were sobering. In 1940 alone, the RAF lost over 1,000 aircraft in combat, with thousands more damaged. The Luftwaffe inflicted similar losses on their own forces. American bomber crews flying missions over Europe would later experience casualty rates exceeding 20% on individual raids. The arithmetic was brutal. Without rapid, effective repair capabilities, the Allies would run out of operational aircraft before they could win the war. This story matters because it illustrates a fundamental truth about warfare and innovation. Victory often belongs not to those with the most advanced weapons, but to those who can maintain, repair, and field those weapons most effectively. The blind rivet, commonly known as the pop rivet, was that force multiplier. It was a seemingly simple tool that revolutionized aircraft maintenance, accelerated production, and ultimately helped determine the outcome of the greatest conflict in human history. To understand the revolutionary impact of the pop rivet, we must first journey back to the early days of aviation and understand how aircraft were actually built and repaired. In the beginning, airplanes were held together by wire, fabric, and wooden struts. The Wright brothers' Flyer, Sopwith Camels, and early biplanes of World War I relied on these materials. But by the 1930s, aviation had undergone a dramatic transformation. Engineers discovered that aluminum alloys offered the perfect combination of strength and lightweight. The age of all-metal aircraft had arrived. Companies like Boeing, Douglas, Lockheed in America, and Supermarine, Hawker, and de Havilland in Britain pioneered stress-skin construction. Instead of fabric stretched over a frame, these new aircraft featured aluminum sheets riveted directly to the internal structure, creating a monocoque design where the skin itself bore structural loads. It was elegant, efficient, and incredibly strong. But it came with a significant challenge. How do you join thousands of individual aluminum panels together? The answer, dating back to ancient Egypt, was the rivet, essentially a metal pin with a head on one end. You'd drill a hole through 2 pieces of material, insert the rivet, and then deform the headless end with tremendous force, creating a second head that clamped everything together. The process was called bucking, and it required 2 skilled workers operating in perfect coordination. Here's how it worked on an aircraft factory floor. The riveter would stand on one side of the aluminum sheet with a pneumatic rivet gun, essentially a jackhammer that delivered rapid hammer blows at the manufactured head of the rivet. On the opposite side, the bucker would press a heavy steel bar, the bucking bar, against the protruding shaft of the rivet. The gun would hammer against one side while the bucking bar resisted on the other, deforming the soft aluminum or steel rivet into a mushroom-shaped shop head. Done correctly, you'd have a permanent, vibration-resistant fastener that was stronger than the metal it joined. Rosie the Riveter, that iconic symbol of American industrial might during World War II, immortalized this partnership. Women flooded into aircraft factories by the hundreds of thousands, working in pairs to install literally millions of rivets. A single bee, B-29 Superfortress required approximately 600,000 rivets. The B-17 Flying Fortress needed over 400,000. Each one installed by hand. Each one requiring 2 people. But here's the critical problem that emerged as war clouds gathered over Europe. What happens when you can't access both sides of the structure? Consider a damaged aircraft returning from a bombing raid. A Messerschmitt's cannon fire has torn through the fuselage, creating jagged holes that compromise structural integrity. Or flak has peppered the wings, leaving dozens of punctures that affect aerodynamics and fuel tank integrity. To repair these using traditional solid rivets, ground crews would often need to disassemble entire sections of the aircraft, removing access panels, pulling out internal components, sometimes even removing wings or tail sections, just to position a bucker on the blind side of the repair. This wasn't just time-consuming, it was logistically nightmarish. An aircraft repair that should take hours would stretch into days. And in the desperate early years of World War II, the Allies simply didn't have days to spare. Into this crisis stepped an unlikely hero, not a general or an ace pilot, but a Scottish engineer named Hamilton Wylie, working for an obscure Birmingham company that manufactured eyelets for boots and clothing. What Wylie and his partners at the George Tucker Eyelet Company would create would be nothing short of revolutionary. A fastener that could be installed from one side only, blind to the other side of the workpiece. They called it the blind rivet. The world would know it as the pop rivet. The summer of 1940 was Britain's darkest hour. Nazi Germany had conquered France in just 6 weeks, and now the full fury of the Luftwaffe turned toward the British Isles. Hermann Göring, commander of the German Air Force, was supremely confident. He had over 2,600 bombers and fighters at his disposal. Britain's RAF could muster barely 900 operational aircraft. The Battle of Britain raged through July, August, and September. Every day brought fresh aerial combat. Hurricanes and Spitfires rose to meet waves of German bombers escorted by Messerschmitt fighters. The pilots who flew these missions, many of them barely out of their teens, faced terrifying odds. But they fought with extraordinary courage, and slowly, impossibly, they began to turn the tide. Yet for every Spitfire that limped back to base, trailing smoke and glycol coolant from its damaged Merlin engine, riddled with bullet holes and cannon damage, ground crews faced an agonizing calculation. Could they repair this bird in time for tomorrow's sortie? Or would this one have to be cannibalized for parts? The numbers tell a stark story. Between July 10 and October 31, 1940, the RAF lost 1,023 aircraft destroyed and many hundreds more damaged. Aircraft production was ramping up. Lord Beaverbrook, the Minister of Aircraft Production, had taken personal charge and was pushing factories to unprecedented output, but production alone wasn't enough. The RAF desperately needed to keep damaged aircraft flying. Ground Crew Chief Samuel Mackenzie, working at RAF Biggin Hill in Kent, later recalled the crushing pressure. We'd have a hurricane come back with 30, maybe 40 bullet strikes. Holes in the wings, fuselage, everywhere. With conventional rivets, you'd need to get inside the wing cavity, inside the fuselage. Sometimes you'd spend 6, 8, 10 hours on a single repair. And all the while, you're thinking, we need this kite back in the air. The pilots need this kite. Every hour it's sitting here is an hour it's not fighting. The technical challenges were immense. Aircraft structures aren't like automotive bodies or simple sheet metal fabrication. They're complex three-dimensional assemblies with internal stringers, formers, ribs, and load-bearing structures. Wing cavities are narrow, often just inches wide. Fuselage interiors are packed with control cables, hydraulic lines, oxygen systems, and ammunition feeds. Getting a man with a bucking bar into position to support a rivet was often impossible without major disassembly. And disassembly came with its own risks. Every time you removed a wing or opened up a major structural assembly, you introduced the possibility of reassembly errors. Control cables could be improperly tensioned. Hydraulic fittings could leak. Fuel tank seals could fail. The old aircraft maintenance saying was grimly accurate: if it ain't broke, don't fix it, because you might break it trying to fix something else. The Americans faced similar challenges as they ramped up their own war production. Boeing's factories in Seattle were churning out B-17 Flying Fortresses at an accelerating rate. Consolidated Aircraft in San Diego was building B-24 Liberators. North American Aviation was producing P-51 Mustangs. But building aircraft and maintaining them in combat conditions were two entirely different challenges. Major Robert K. Morgan, pilot of the famous B-17 Memphis Belle, witnessed firsthand the Herculean efforts of ground crews maintaining bombers in England. After the Belle's 25th and final mission in May 1943, Morgan wrote, "Those ground crews were miracle workers. We'd come back from Bremen or Wilhelmshaven with the planes shot to pieces. I mean literally shot to pieces, hydraulic lines severed, control surfaces shredded, hundreds of holes in the wings and fuselage. And somehow, those boys would have her ready for the next mission. I don't know how they did it. But the statistics reveal the truth behind that seeming miracle. They couldn't always do it. Not fast enough, anyway." The 8th Air Force, operating from England, lost 4,754 aircraft during the war. Beyond those losses, thousands more sustained damage severe enough to require major repairs. Without adequate repair facilities and efficient repair methods, those damaged aircraft would sit idle, reducing available strength for missions. The Soviet Union faced perhaps the most acute version of this problem. Operating on the Eastern Front with limited industrial infrastructure, Soviet maintenance crews improvised desperately. They lacked proper tools, facilities, and often even spare parts. German pilots reported seeing Soviet fighters held together with wire, fabric patches, and sheer determination. One German ace, Erich Hartmann, described shooting down a Yak-9 fighter that appeared to have been repaired with what looked like hammered tin cans and prayer. Even before America entered the war, military planners recognized the looming crisis. A 1940 U.S. Army Air Corps study concluded that for every aircraft in combat, the service would need a 3-to-1 ratio of support infrastructure, including repair facilities, spare parts, and trained personnel. The math was daunting. If you wanted 1,000 bombers over Germany, you needed infrastructure to support 3,000 aircraft total. The bottleneck was clear. The question was, could anyone solve it? Hamilton Wylie didn't set out to win a war. Born in Scotland in the late 1880s, Wylie was trained as an engineer with a particular fascination for mechanical fasteners and joining methods. In 1916, during the First World War, Wylie was working for the Armstrong Whitworth Aircraft Company, one of Britain's premier aircraft manufacturers. The aircraft of 1916 were still largely wood and fabric constructions, but forward-thinking engineers like Wylie could see the future. Metal would dominate. And metal construction presented unique challenges. Wylie began experimenting with a radical concept. What if you could install a rivet from just one side of the workpiece? His initial design was elegant in its simplicity. The rivet consisted of a hollow tubular body and a pull-through mandrel, essentially a long pin that extended through the center of the rivet. The installer would insert the rivet into a pre-drilled hole, then use a special tool to pull the mandrel. As the mandrel pulled through the hollow rivet body, it would deform the blind side, creating a second head. The installer never needed to access the back side of the work. Wylie patented this concept, but the technology wasn't quite ready. His early rivets required the mandrel to be secured with a nut on the backside, which partially defeated the purpose. The tool designs were cumbersome. And most critically, the world wasn't ready for all-metal aircraft construction yet. Fast forward to the 1920s. Aviation was evolving rapidly. Hugo Junkers in Germany had pioneered all-metal corrugated aircraft. In Britain, companies like Armstrong Whitworth were transitioning to stressed skin designs. Wylie, now working as a consultant, approached the George Tucker Eyelet Company of Birmingham. George Tucker Eyelet Company had been founded in 1885 and specialized in making small metal components, eyelets for shoes and boots, hooks, grommets, and similar hardware. They had expertise in working with soft metals and forming operations. They also had vision. When Wylie presented his blind rivet concept, the company's engineers saw its potential. Between 1928 and 1934, Wylie and Tucker's engineers refined the design. The breakthrough came when they developed a mandrel with a precisely engineered weak point, a small notch partway up the shaft. Here's how the finished product worked. The rivet body was a hollow aluminum tube with a manufactured head on one end. The mandrel, a steel pin, extended through the entire length of the rivet and protruded from both ends. To install it, a mechanic would drill a hole through both pieces of material to be joined. They'd insert the rivet from the accessible side, pushing it all the way through until the manufactured head sat flush against the material. Then came the magic. Using a specialized tool, essentially a pistol grip device with internal gripping jaws. The mechanic would grab the protruding mandrel and squeeze the trigger. The tool would pull the mandrel back through the rivet body. As the thick head of the mandrel was dragged through the hollow rivet shaft, it would deform the aluminum, expanding it outward. On the blind side of the workpiece, the rivet body would bulge out, forming a crude but effective second head. The two pieces of material were now clamped between the manufactured head and this newly formed blind head. The mechanic kept squeezing. Pressure increased. The rivet body expanded more, filling the hole completely and clamping down tight on the materials. And then, pop! The mandrel shaft would break at the engineered weak point, separating cleanly. The excess mandrel fell away or was collected. What remained was a fully installed, permanent rivet, and the entire process had taken seconds. They called it the pop rivet, after that distinctive popping sound when the mandrel broke. The trademark was registered. Production began, initially targeting industrial and automotive applications. But everything changed in 1939. Two critical developments converged. First, in the United States, the first patent for an aluminum blind rivet suitable for aircraft applications was issued. Second, Germany invaded Poland, and the world went to war. The British Air Ministry, Ministry of Aircraft Production, and the RAF moved with unprecedented urgency. They'd been watching blind rivet development and immediately grasped its implications. If ground crews could repair battle damage from one side only, they could slash repair times dramatically. If aircraft manufacturers could use blind rivets in certain applications during production, they could simplify assembly and reduce man-hours. George Tucker Eyelet Company shifted to wartime production. Their Birmingham factories, which had been turning out modest quantities of rivets for commercial applications, transformed into a critical munitions supplier. Women and older men, the young men had gone to war, staffed the production lines. The machinery ran day and night. The numbers that emerged from this period are staggering. Between 1939 and 1945, George Tucker Eyelet Company and other manufacturers produced 3 billion blind rivets for the war effort. 3 billion. That's not a typo. To put that in perspective, the entire Allied production of tanks during World War II was approximately 227,000 units. Aircraft production totaled around 750,000. But rivets? 3 billion. Those rivets found their way onto virtually every Allied aircraft. RAF ground crews working on damaged Spitfires and Hurricanes during the Battle of Britain used them to patch fuselage damage. American maintenance units attached to the 8th Air Force in England used them to repair battle-damaged B-17s and B-24s overnight, getting the bombers back into formation for the next day's raid. Navy crews on aircraft carriers in the Pacific used them to fix Dauntless dive bombers and Corsair fighters between missions. The time savings were revolutionary. A repair that might have required 2 men working 6 hours with conventional rivets could now be accomplished by 1 man in 30 minutes. That's a 90% reduction in labor hours. And remember, in combat, every hour counts. Technical Sergeant James Hardesty, assigned to the 303rd Bomb Group, the Hells Angels, at Molesworth, England, left a vivid account in his wartime diary. February 19, 1944. The vicious virgin came back today from Frankfurt shot to hell. Counted 83 holes in her, including 2 the size of basketballs in the port wing. Usually a plane this bad would be grounded for a week, maybe more. But with these new pop riveters, we had her patched, tested, and ready for the mission board by 0400 next morning. 16 hours, not a week. That bird flew to Regensburg the next day and came back safe. Those rivets saved her. They've saved a lot of birds. The British pilot Hugh "Cocky" Dundas, who flew Spitfires during the Battle of Britain and later commanded fighter squadrons, wrote in his memoir, "We pilots owe an enormous debt to the ground crews who kept us flying." And they, in turn, owed a debt to whoever invented that marvelous pop rivet. I never much thought about it during the war. You didn't think about rivets when you were trying not to be shot down. But looking back, I realized those simple little fasteners were as important as radar, as important as the Merlin engine. Maybe more so. The innovation spread globally. By 1942, American manufacturers had licensed the technology and were producing millions of blind rivets domestically. The Soviet Union, receiving technical specifications through Lend-Lease, began their own production. Even the Japanese, despite being an enemy power, had developed parallel technology, though their version was reportedly less reliable. The impact of the blind rivet on World War II is difficult to quantify precisely, but its effects rippled through every aspect of Allied air operations. Let's examine the evidence systematically. Aircraft production acceleration. Boeing's wartime production records reveal that the introduction of blind rivets in certain assembly processes reduced man-hours per aircraft by 15 to 20%. When you're building 12,731 B-17 flying fortresses over the course of the war, a 15% reduction in assembly time translates to getting approximately 1,900 additional bombers into service over the same time frame. Those aren't hypothetical numbers, they're lives saved and missions accomplished. The British Civilian Repair Organisation, CRO, established in May 1940 under Lord Beaverbrook's Ministry of Aircraft Production, provides even more dramatic evidence. The CRO coordinated civilian companies in repairing damaged RAF aircraft. Between May 1940 and July 1945, the CRO returned 79,000 aircraft to operational status. Internal CRO reports indicate that blind rivets were critical to achieving this volume. Where traditional repair methods might take days, blind rivet repairs could be measured in hours. Consider this statistic. By July 1945, 36.5% of all heavy aircraft then flying in the RAF, some 3,285 aircraft, had been processed through CRO facilities. Without rapid repair capabilities enabled by innovations like blind rivets, a significant portion of RAF bomber strength simply wouldn't have existed. Operational readiness rates. The U.S. 8th Air Force, conducting strategic bombing campaigns over Europe, maintained detailed records of aircraft availability. In 1942, operational readiness rates, the percentage of aircraft available for missions on any given day, averaged around 60%. By 1944, despite more intensive operations and heavier combat damage, operational readiness had improved to nearly 75%. Multiple factors contributed, but maintenance efficiency was paramount. A 1944 technical report from the 8th Air Force Composite Command stated, "Rapid battlefield repair capabilities utilizing single-side access fasteners have proven essential to maintaining combat strength." Units equipped with pneumatic blind rivet installation tools report average repair times 70 to 80% lower than comparable units using conventional methods. The Pacific Theater experience. The island-hopping campaigns in the Pacific presented unique challenges. Forward air bases were often primitive, little more than bulldozed coral runways with minimal facilities. Maintenance crews worked in brutal conditions, intense heat, high humidity, and the constant threat of enemy attack. Under these circumstances, speed of repair became paramount. Operation Ivory Soap, declassified in 1953, revealed one of the war's most remarkable logistics innovations. The U.S. military converted Liberty ships into floating aircraft repair facilities. These ships, equipped with complete workshops and staffed by thousands of specially trained personnel, could anchor near forward bases and conduct major repairs. Blind rivets were central to this capability. They allowed repairs in the cramped confines of a ship's hold where traditional bucking operations would have been impossible. These floating repair units processed thousands of aircraft. Lieutenant Commander Harold Jensen, who served aboard one such vessel in 1944, recalled, "We'd get planes barged out to us that had been written off as total losses. Corsairs with wings almost torn off, Hellcats with fuselage damage that looked catastrophic. And we'd rebuild them. The pop rivet was our best friend. You could work in spaces where you couldn't fit two men. One man, one rivet gun, and you could patch anything." The strategic dimension. Beyond the tactical benefits, blind rivets contributed to Allied strategic superiority in less obvious ways. Simplified maintenance meant that aircraft could be deployed farther from major repair depots. It meant that smaller, more mobile maintenance units could keep pace with advancing forces. It meant that aircraft damaged in remote locations, the jungles of Burma, the deserts of North Africa, the frozen airfields of Alaska, could be repaired locally rather than being written off entirely. German forces, despite their technical sophistication, never developed blind rivet technology as extensively. Luftwaffe maintenance protocols remained wedded to traditional methods. German aircraft historian Werner Bombach noted in his post-war memoirs, "Our maintenance procedures were thorough and professional, but inflexible. We lacked the Americans' genius for expedient field repairs. Too often, a Messerschmitt or Focke-Wulf with moderate battle damage would be grounded for days awaiting depot-level repairs. The enemy would have such an aircraft back in combat within hours." Human stories. The The statistical evidence is compelling, but it's the human stories that really illuminate the rivet's impact. Flight Officer Margaret Kerr served with the Air Transport Auxiliary, ferrying new and repaired aircraft from factories to operational squadrons throughout Britain. Her 1944 diary includes this entry: picked up a Hurricane Mark IIC from Langley today. Absolutely covered in those little pop rivets. They call them that because they make a popping sound when installed. The ground crew chief told me this particular kite had been shot down over the channel 2 months ago, ditched, salvaged, and rebuilt. Without those special rivets, he said, she'd have been scrapped. Instead, she's flying again, and some pilot will take her into combat. Makes you think, doesn't it? About the little things that matter. Sergeant Antonio DeMarco, assigned to the 15th Air Force in Italy, wrote home in March 1945, "Ma, you asked me what I do in the war. I fix planes. Not the glamorous job, not like being a pilot. But last week, a B-24 named Jersey Bounce came back from a mission with over 100 holes. The crew thought she was done for. We worked all night with those new rivets the Army gave us. Next morning, Jersey Bounce flew her next mission. Pilot came by later, shook my hand, said we saved his ship. That's what I do, Ma. I save ships so they can save lives." Technological legacy. By war's end, blind rivets had become standard throughout aviation. But their influence extended far beyond aircraft. Post-war, the technology found applications in automotive manufacturing, appliance production, construction, and countless other industries. That distinctive pop sound would become one of the most common noises in manufacturing worldwide. The British government, recognizing George Tucker Eyelet Company's contribution, awarded them special commendations. Hamilton Wylie, the original inventor, lived long enough to see his concept prove decisive in history's greatest conflict. He died in 1948, relatively unknown outside engineering circles, but his legacy was already secured. The ultimate measure of the blind rivet's impact might be this. After the war, no one ever seriously suggested going back to purely conventional rivet methods. The innovation was too useful, too efficient, too essential. It had permanently changed how things were built and repaired. 75 years after the end of World War II, the pop rivet remains ubiquitous. Walk through any aircraft factory, whether Boeing in Seattle, Airbus in Toulouse, or Embraer in Brazil, and you'll hear that distinctive pop dozens of times per minute. Despite advances in composite materials, adhesive bonding, and welded structures, the blind rivet continues to play a critical role in modern aircraft construction and maintenance. The principle of accessibility. The blind rivet taught engineers a fundamental lesson. Accessibility matters as much as strength. It doesn't matter how strong or elegant your fastener is if mechanics can't physically install it in real-world conditions. This principle extends far beyond rivets. Modern design philosophy emphasizes maintainability, ensuring that systems can be serviced, repaired, and upgraded easily. Contemporary aircraft like the F-35 Lightning II or Boeing 787 Dreamliner incorporate maintenance accessibility into their fundamental design. Access panels are strategically placed. Systems are modularized. Fasteners are selected not just for strength but for ease of removal and installation. This mindset traces directly back to the lessons learned with blind rivets during World War II. Innovation from unexpected sources. Hamilton Wylie wasn't working for the Air Ministry or a major defense contractor when he invented the blind rivet. He was a consulting engineer working with an eyelet manufacturer. George Tucker Eyelet Company made hooks for shoes. They weren't in the business of winning wars, but they had capabilities, vision, and willingness to innovate. This pattern repeats throughout history. Radar was developed by physicists studying the ionosphere. Penicillin was discovered accidentally by a bacteriologist studying mold contamination. The Internet emerged from academic computer science research. GPS evolved from military satellite navigation experiments. Often, breakthrough innovations come from adjacent fields or unexpected sources. The lesson for modern innovation is clear. Don't limit your search for solutions to obvious places. The company making eyelets might have the answer to your aircraft maintenance problem. The computer science researcher might solve your logistics challenge. The medical device manufacturer might contribute to automotive safety. Innovation thrives at intersections. Speed matters in crisis. When the Battle of Britain raged, the RAF didn't have the luxury of years-long development programs. They needed solutions immediately. The blind rivet was ready, or nearly ready, and was rushed into service. It wasn't perfect initially. Early versions had reliability issues. The tools were crude. But it was good enough, and good enough was infinitely better than nothing. Modern military strategists and business leaders face similar pressures. In crisis, perfect becomes the enemy of good. The ability to rapidly deploy imperfect but useful solutions often determines success or failure. This doesn't mean abandoning quality or safety standards, but it does mean recognizing that sometimes 80% of the optimal solution available today beats 100% of the optimal solution available next year. Compound effects of small improvements. A single blind rivet saves, perhaps, 30 minutes compared to traditional methods. Seems modest. But multiply that across thousands of rivets per aircraft, hundreds of aircraft being repaired simultaneously, over years of combat operations, and you've just created thousands of additional combat-ready aircraft that otherwise wouldn't have existed. Businesses call this marginal gains, the accumulation of small improvements that compound into massive advantages. British cycling famously used this philosophy to dominate international cycling, making tiny improvements to every aspect of training, equipment, and nutrition. Amazon built an empire partly on obsessively optimizing every millisecond of its website's load time. The blind rivet was a marginal gain that became a war-winning advantage. The invisible infrastructure of victory. When we think about World War II technology, we picture Spitfires, Sherman tanks, and atomic bombs. We don't picture rivets. Yet rivets, specifically blind rivets, were arguably more important to Allied victory than many weapon systems that receive far more attention. This highlights a profound truth about complex systems. The infrastructure matters as much as the headline technology. Your fighter plane is useless if you can't repair it. Your battle tank is worthless if it can't be maintained in the field. Your nuclear bomb doesn't help if you can't deliver it. Modern militaries understand this. The U.S. military spends enormous resources on logistics, maintenance, and sustainment. For every F-22 Raptor fighter jet costing $150 million, the Air Force maintains supply chains, training programs, maintenance facilities, and support systems worth hundreds of millions more. The visible weapons platform is just the tip of the iceberg. Democratization of capability. Traditional riveting required two skilled workers operating in perfect coordination. It required training, practice, and teamwork. Blind rivets democratized aircraft repair. A single mechanic with basic training could install them. This had profound implications for wartime production and maintenance. With labor forces depleted by military conscription, Britain and America relied heavily on women, older workers, and individuals who would never have been hired for skilled manufacturing in peacetime. Blind rivets' relative simplicity enabled these workers to contribute effectively. The technology lowered the skill barrier without compromising quality, a powerful example of how good design can expand the pool of capable practitioners. This principle remains relevant. User-friendly interfaces, simplified tools, and intuitive designs allow more people to accomplish complex tasks. The smartphone revolution happened partly because Apple and others made powerful computing accessible to non-technical users. Wikipedia succeeded because it made publishing accessible to anyone. YouTube enabled everyone to become a broadcaster. Good design removes barriers. The blind rivet was good design. The long game of innovation. Hamilton Wylie patented his blind rivet concept in 1916, but it didn't achieve widespread adoption until the 1940s. That's nearly 25 years from invention to impact. Why so long? The technology needed time to mature. Manufacturing processes had to be refined. The market, all-metal aircraft construction, needed to develop. Tools and techniques needed to evolve. Many innovations follow similar timelines. The transistor was invented in 1947 but didn't revolutionize electronics until the 1960s. The Internet's foundational technologies were developed in the 1970s but didn't transform society until the 1990s. Lithium-ion batteries were invented in the 1970s but only recently enabled electric vehicle revolution. The lesson: don't dismiss innovations just because they haven't achieved immediate impact. Technologies often need time to mature, find their proper application, and combine with other developments to reach their potential. Patience and persistence matter. Institutional adoption and resistance. Despite clear evidence of blind rivet's effectiveness, some military units and contractors initially resisted adoption. Traditional-minded engineers questioned their strength. Some mechanics, proud of their bucking skills, saw them as threatening their expertise. Procurement officers worried about supply chains and quality control. This resistance gradually collapsed under the weight of evidence and wartime necessity. But it's a reminder that even obviously superior technologies face adoption challenges. Established practices, institutional inertia, and human psychology create friction against change. Modern change management research confirms this pattern. Studies show that technological superiority alone rarely ensures adoption. Social factors, trust, perceived fairness, ease of learning, and institutional support matter enormously. The blind rivet succeeded not just because it worked, but because advocates within the RAF and Air Ministry championed it, because training programs were developed, because supply chains were established, and because proof-of-concept demonstrations convinced skeptics. If you're trying to introduce innovation in your own organization, remember this lesson. Technical merit is necessary but insufficient. You need champions, you need training, you need to address legitimate concerns, and you need to demonstrate value clearly and repeatedly. The ripple effects continue. Today, if you board a commercial airliner, elements of that aircraft structure almost certainly incorporate blind rivets. If you drive a modern automobile, blind rivets hold together portions of the body or interior. If you work in a modern office building, the HVAC ducts, suspended ceilings, and countless other components were assembled with blind rivets. The global market for blind rivets exceeds $4 billion annually. Millions of workers across hundreds of industries use them daily. They've become so commonplace that we don't even notice them. That's perhaps the greatest tribute to their success. They've become invisible through ubiquity. Yet their origin story remains extraordinary. A Scottish engineer's clever idea, refined by a Birmingham Eyelet company, rushed into service during humanity's darkest hour, and proving decisive in determining the outcome of history's greatest conflict. Personal reflections. I'm struck by the humility of this story. No one erected monuments to the pop rivet. Hamilton Wylie doesn't have his face on currency. The workers at George Tucker Eyelet Company who produced 3 billion rivets didn't receive parades. The ground crews who used those rivets to keep Allied aircraft flying rarely received recognition beyond their units. Yet their contribution was immense. Every bomber that struck German industrial targets, every fighter that protected those bombers, every reconnaissance aircraft that provided intelligence, every transport that carried supplies, they all depended on those simple aluminum fasteners. War is often remembered through the lens of heroes, battles, and dramatic moments. The fighter ace, the bold general, the pivotal invasion, these capture our imagination. But wars are won through the accumulation of countless small advantages. Better logistics, more efficient production, faster repairs, superior training, more effective intelligence. The unglamorous background work that enables dramatic foreground action. The blind rivet represents all of that invisible infrastructure of victory. It reminds us that innovation isn't always about revolutionary new weapons or dramatic technological breakthroughs. Sometimes it's about finding a better way to solve a mundane problem. Sometimes it's about eliminating a bottleneck. Sometimes it's about making existing systems work better, faster, and more efficiently. The enduring question, looking back across 8 decades, we can ask, what are today's equivalents? What simple tools or techniques could dramatically improve critical systems but remain undiscovered or underutilized? What innovations are languishing in obscurity, waiting for the right crisis or the right champion to bring them into widespread use? The blind rivet teaches us to look for answers in unexpected places, to value practical solutions over elegant theories, to embrace good enough when perfect isn't available, and to recognize that small improvements, consistently applied, can change the world. A final thought. In researching this story, I came across one last account that seems fitting to share. In 1995, 50 years after the war ended, a group of British veterans gathered at the Imperial War Museum in London. Among them was Arthur Cummings, who had served as a ground crew chief with RAF Bomber Command from 1942 to 1945. A reporter asked him what he remembered most about the war. Cummings thought for a moment, then said, "The sound. That popping sound. Must have heard it a million times. Every pop meant another rivet going in, another patch being made, another aircraft getting closer to flying again. We'd work through the night sometimes, and all you'd hear was pop, 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 echoing across the airfield. It was the sound of hope, really. The sound of us refusing to give up. The sound of us winning. That's what I want you to remember from this story. Innovation doesn't always announce itself with fanfare. Sometimes it arrives with a simple pop. But that pop can echo through history.